Today we're going to look at derivatives and integrals and how those relate to differentials. So recall what the derivative is. It's defined as the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Well, if you look at the top, f of x plus delta x minus f of x, if y is equal to f of x, then that's not anything but delta y. And if you think about what f prime of x is, another notation says what? It's df dx. So the point is, we can think of df dx as a limit as delta x tends to 0 of what? Delta f, change in f, over delta x, change in x. Equivalently, if y is f of x, then this is just delta y over delta x. Limit as delta x tends to 0. So what's the point? That the derivative, dy dx, is a limit as delta x tends to 0 of delta y over delta x. So as delta x goes to 0, delta y turns into dy and delta x turns into dx. Coincidence? No. So in other words, delta y and delta x in the limit can be thought of as dy and dx. Now this turns out to even be true in the setting of integration. Recall that when defining a definite integral, it represents the area under the curve as it's computed as a sum of small rectangles. And you might have seen that when definite integrals were first introduced. It's called a Riemann sum. So the integral from a to b of f of x dx is really the signed area under the curve. And I say signed because why? If the function is under the x-axis, it computes the area negative. If it's on top of the x-axis, it computes it as positive. So how is a definite integral defined? Well, as a Riemann sum. So you take one of these small little differential rectangles of width what? Dx, and height what? F of x, and you add them all up. So the integral from a to b of f of x dx is defined as the limit as delta x tends to 0 of the sum of all these little areas. And then you take the limit as the width of these rectangles goes to 0. So in fact, this is the definition of a definite integral in terms of a Riemann sum. Now, if we split up all these little rectangles with equal width, the width is going to be this length, b minus a, that's the length of this interval here, all over how many rectangles we want, in, and xj just really has to be inside of each of these intervals. Sometimes you do the left-sided limit, sometimes you do the right-sided limit, sometimes you take the max length or the minimum length in an interval. But the point is that when you let delta x tend to 0 and n then goes to infinity, that all of those converge to this signed area. And so, if you notice, in the limit, as delta x goes to 0, sigma, which stands for sum, both start with s, get it? Turns into the integral, which looks an awfully lot like an s. And just like we saw before, here the width, delta x, turns into a differential dx. So in the limit, as delta x tends to 0, sums turn into integrals, and deltas turn into differentials. So the concept of delta x and delta y becoming dx and dy in a particular limit is a recurring theme that we will be talking about again and again for the rest of the semester. I'd like to say just in passing that this even manifests itself in Newton's method, which is a way one has of estimating the zero of a function. But that's for another time. I think I will stop here.